This is the first part of the lecture 4. Oh, sorry, it's already 4. And part A, 4A. And today topics are, let's say, today's topic is the Laurent series. So let me write it down. Sorry, I have to put the proper Laurent series. So what is a Laurent series? So Laurent series is a power series that has both let's say positive powers and negative powers. So maybe let's say like this: the series of the type. And now let me write it down. The series looks like this. This is n, starts at minus infinity, goes to the plus infinity, and I put here an, and this will be z minus z0 to the power n, is called a Laurent series. So notice that actually we can write such a series. Notice that the above series can be written in a way that we can separate, let's say, positive powers from the negative powers in form. So let me just simply copy this one. So this is n is equal minus infinity, an, and this is z minus z0 to the power n, and start n is equal 0. So this is the portion of this Laurent series which is just a regular power series. Plus, and I put here plus a little lower, plus, and this will be like again, the starts at 1, so 1 to infinity, and those are the negative powers. So I put it like that. Maybe let's write it down this way, right? It's not just, okay. So this will be a minus n, and here we divide it by z minus z0 to the power n. So here the positive powers, and this is negative powers. So since that one and that one are just simply very similar, so we know when it will converge. So for example, we know that for given, if you have here if, so put it like this: if the z minus z0 smaller than r, call it r2. This is the radius of convergence of the first series, 1, right? 10, this was actually convergence series, so this gives you a number. And if 1 over z minus z0 smaller than rho, and this is the radius in certain way of convergence, you see, because negative powers, you can still take it like a little power and apply the test, like one of the tests, you will find out that gives you the radius of convergence for the second series, okay, 10, if R2 is actually strictly larger than, call this R1, and I write it down, that one will be divided by rho. Wow. So that means we have here, we have a region of convergence, a region of convergence for this series star. So call that one star. So So this one is a star. So this is the Laurent series star. How it looks like. So okay, so we have here Z0 is here, and here we have here smaller radius. This is my R1, which is indicated here. This is my R1. Yeah, you see this, that means that one is equivalent to say that Z minus Z0 must be larger than 1 over rho. Then the series is convergent. I call it R1. And then you have here the second circle. Yeah. Around Z0. This is the larger circle. And the radius here is R2. This is R1. So the series is convergent, okay? Let's shed this region of non-convergence. Here we don't have convergence, but we have the convergence which is exactly inside this annulus. So this is annulus. So the domain of convergence of such a Laurent series, so the Laurent series star converges inside this region D, which is the set of all Z, such that here we have R1 smaller, and this is Z minus Z0, and this one is smaller than R2. Yeah, so that's the region. If this is convergent, so that means for every Z belonging to that one, so that means if Z belongs to D, then we have a function f of Z, which is given by this particular Laurent series, is convergent and gives you the value. So we are getting a function, like in the case of the regular power series. So this function. So in such a case, notice that this function is analytic in this region. So notice this is for Z belonging to D, that f of Z actually is analytic inside D, and you know how to compute this derivative. So you will do exactly the same way as we do it all the times, namely you can see that this derivative can be obtained by using the differentiation term by term and minus infinity, and then you have here a and Z minus Z0 to the power, which of course gives you this formula. This is n is equal minus infinity, this will be a n times n, and this will be Z minus Z0 n minus 1. So term 0 of course will disappear. So this derivative exists, yes. So it's an analytic. Of course, if you can differentiate term by term, the same things will apply by the same principles to the integration term by term. So if so in certain way, if a function f of Z can be represented inside a certain annulus D contained in the domain of the definition of f, then we will say that f of Z has an expansion into Laurent series in D, centered at Z0. So this is the Z0. So let me point you out, that's the Z0, that's the Z0, and this is the annulus. Okay, so let's see, let's make an example, let's do some examples. So let's say, find something, let's find something, let's see if I have, okay, so let's do it, example. Find a Laurent expansion, the Laurent expansion of the function and let me write it down, f of z equals, and put it like this, this is z minus a, so here a is a fixed number, constant number, around the given point, and I will just write this point to be z0, any point, different than a, just to make sure this is different than a. Possibly a, why not? Possibly a. Also possibly a, yeah, given point. Okay, so what is the situation here? Picture. So this is my coordinate system. So this is my plane, complex plane. I know that the domain of the function, so put it like this. This is my point A. So this is not in the domain. So that means write it down. Domain of f is equal to C, and you remove the point A. So that point is not in the domain. Now, let's say I have here a point Z0 here. This my point is Z0. So there are two possibilities. So if you see, you have here first one, you have this annulus, which is actually a disk. Maybe I'm making it ugly picture. So this is the first annulus, call it D1, and then you have another annulus, the outside that one of the dotted circle. So this is D2. So here would be the first one. So let me shed it in red. So the first annulus is here. But you see, in that place, if you do the expansion will be just the Taylor series. So has a Taylor series. So the Taylor series is of course also a Laurent series, yeah, with no negative terms, but still it's a Laurent series. So that means this Taylor series gives you the answer in the domain D1, and we know how to do it. We did it in the previous classes, we expanded it. So we are looking for the expansion. So we are looking for the Laurent series expansion of f of z in the second one. So what is the second one? So the second one is in D2, which is the domain, the set of all z, such that first of all you have here the distance of z0 minus a, that's the radius of the dotted circle here, and this must be, and that must be larger than z minus z0. So that one in this way. So this is outside, this is D2. And how we are going to do it? So the idea is very simple. Geometric series. We will use the geometric series. So how do we do it? Just simply watch this. I take 1, and this is z minus z0. A, that's our function. Maybe let's properly. F of z is equal 1 minus z minus a. okay, f of z is equal 1 z minus a, and now I write it down like this. Look what I'm doing. I'm writing down that this one is equal z minus z0, and then I write it down minus, and that one means a minus z0. Yeah, that's the same here. Clearly, you see, that one will cancel that one, so that's correct. And now, since I look at the picture, and what do I see? On the picture, I see that, where is my, oh yeah, so my z now belongs here, so this is my z, and then I have here the one distance is here, that distance is here, so the distance between z and z0 is larger than the other one. So in such a case, if you see, that one will be the larger one, larger, and that one will be smaller. So I will pull out the larger one. So I will get this expression. So I put here z minus z0, and now I put here, this will be 1 minus a minus z0 divided by z minus z0, put here 1, and now I look at this one and I say this is my cube, and I can see by the remark that since z minus z0 is strictly larger than a minus z0, we have here that this cube is strictly smaller than 1, so we can use it as a geometric series that 1 minus q equals kn is equal 0 to infinity q to the power n. So the same trick as before, and we obtain that this is equal, this is z minus z0, and then here the geometric series n is equal 0 to infinity, and then we have here a minus z0 to the power n divided by z minus z0 to the power n, which gives me the answer. This is equal, and this is n is equal 0 to infinity, and then you have here a minus z0 to the power n 1, and this is z minus a z0 to the power n plus 1. So since this is a n plus 1, clearly that number here is the coefficient a minus n plus 1, because that power is negative. No, we can rewrite it actually. We can rewrite it, but let's say that's not necessary. We will basically rely on this example as a kind of a model how to look for such Laurent series. So now, of course, yeah, the example is finished. So let's formulate our main result. Let me see where we are. Okay. Yeah. Okay. Maybe couple of more examples. Example number 2. Example 2. So let's say like this. Find the Laurent series of the functions of the following functions. So I put here a f of z is equal e to the minus 1 over z. Very good. And the second one, b, f of z is equal to, cosine 1 over z squared. So solution. Notice that we actually know what is the power series expansion of the e to the power z. So this is n is equal 0 to infinity and this is z to the power n divided by n. So by simple substitution, so by substituting z by minus 1 over z, we obtain the answer. So we just obtain that our f of z is equal e to the minus 1 over z is equal, and I'm getting the Laurent series, which is minus 1 to the power n divided by n factorial, and this is 1 and this is z to the power n, z to the power n. And that's the Laurent series. So clearly this coefficient is a minus n, so those are the coefficients corresponding to the negative powers. And similarly, so this is my a, so this is my a. In similar way, to solve b, I take cosine of z, and I know what is the power series expansion of this. At the zeros, it will be equal to minus 1 to the power 2, and this is zn to n, and this is 2n factorial. So now, again, by substitution, z by 1 over z squared, we obtain that our f of z, which is equal cosine 1 over z squared, equals, and here we are getting n is equal 0 to infinity minus 1 to the power n divided by 2n factorial, and the powers are negative. So what are the powers here? So powers are z to the power 2 to the power 2n, so that's 4n. So maybe let me just simply write it. Z to the power 4n. Z to the power 4n. Okay, so we got this example. So now let us formulate. Maybe I go to the new paper, and let's formulate the main theorem for today's class. So this will be theorem let f from, okay, let's start maybe like this. Let D be a domain. Let D be a domain in C, and f from D to C, an analytic function such that an annulus, put it like this, annulus, so such that A, which is equal to the set of all Z, satisfying the property that, call that one like a R1, smaller than Z minus Z0, smaller than R2, is contained in D. Is contained in D. So we have here this annulus. So this is the annulus. Okay, maybe picture. So here we have the D. This is my D. This is my D. I remove something from here. So this is removed. This is removed. This is my D. And now I take the point. Okay, let's say Z0 is here, and that's not nice. Z0, and then I have a circle here, little circle. That's my first circle, and then I have another circle. Still ugly. Now it's better. So this is the radius R1, this is the radius R2, and that's my annulus A. So that's this guy. This is A. Okay, maybe such that this annulus. 10 f of z has a Laurent series expansion in A such that, let's write it down this expansion, such that this f of z can be written as a convergent series, and put it like this: n is equal minus infinity to infinity, and this will be a n z minus z0 to the power n. And we are able actually to give you the formula for this a n, namely, I need to do something, I need to change color. Namely, I can actually choose any circle here, gamma, positively oriented around the z0. So gamma is this circle around the z0 inside A. So say like this: gamma equals to z0 plus REIT. T belongs to, oh, I cannot squeeze it here. So put it here. Gamma is equal to z0 plus REIT. T belongs to 0 to pi, and R is between R1 and R2. So in such a case, this AN can be written, this is just simply 1 over 2 pi I, and then integral over gamma, and I put here FW dW, and here the same formula as last time, n plus 1, exactly the same formula, n plus 1, where n is equal 0 plus minus 1 plus minus 2, and so on. Wow, so this is the power series expansion, then this Laurent series expansion of this one. So that's actually almost similar, except now it can be negative powers and positive powers. So let me write down proof. Okay, we'll make a picture of annulus. So let's keep it. So my z0 is here, and then we have a smaller circle. So call this smaller circle gamma 1. Ugly. Sorry. Smaller circle. Okay, let's say let's say cut it off, and this is my annulus. So I will not denote. So this is annulus. So this is my A. So this is also taken away. That's taken away. I love that part of the lecture, making really nice abstract drawings. Actually, if you look at the modern art, you could consider this as a kind of a, let's call it like a challenge, artistic challenge. So 10, I can take any point Z. So I take point Z belonging here. So this is any point. Z belongs to A. And I want to represent it here, this as the value of this function f as the Laurent series. So what do? I take the circle, big circle, you see, but it's still smaller than this dotted circle. No, I'm not supposed to touch. I'm not supposed to touch the border. Ugly. Again. Good. So this is the circle. Call this circle because it's bigger. Call it gamma 2. It goes that way. And the other circle, smaller, so, and call it gamma 1 because it's smaller. Gamma 1. So look, Z0 is exactly in the middle of it. And denote and call this region, G, in between the red circle. That's the region C. So in such a case, if I would like to write down what is the boundary of this region, so I will say the boundary is exactly the contour which is equal to gamma 2 minus gamma 1, because the orientation will change on gamma 1. That's this way, and you need another one. So that's why it is equal to this. So now we have here the Cauchy integral formula again. Let's use the Cauchy integral formula. So by Cauchy integral formula, the function f of z can be written exactly as the 1 over 2 pi I, and this is integral over boundary of g, and this is f w, and this will be w minus z, sorry, dw, dw. So that's the Cauchy integral formula. And that one, use the fact that the boundary is that one, use the properties of this integral, I can write exactly as two integrals. First integral will be around the gamma 2, and this is fw dw divided by omega minus z. And the second one, so put it like this, plus, it will be plus 1 over 2 pi I, and that will be minus gamma 1 f dw, and the same thing, minus z. Then, of course, this is the orientation here. This is the orientation here that is changed. So I have to rewrite it again. So write it down, put it like this, 2 pi I, and then write it down. This is gamma 2, unchanged. I copy it, just copy it. And this is w minus z. And this will be minus, of course, minus 1 over 2 pi I. And let me go down. Integral of gamma 1 f of w dw d minus z. If you remember what we have done during the proof of the Taylor expansion formula, if you remember, then you will immediately recognize that we are doing exactly the same. First of all, here we have the same situation, so let me just simply continue. So the first 2 pi I integral, I do it like this. I take gamma 2, and then I put here f omega here, and then I rewrite the second thing is like w minus z0 minus z minus z0. Yes, dw. And then I have minus, and the second integral, why not? I do the same. This is gamma 1, and this will be f w, and I put here the same. W minus z0 minus z minus z0, and I put here dw. 10, I look at the picture. Where is gamma 2? Gamma 2 is here, so W belongs here. Z belongs here. So we have two distances. So one distance is from Z0 to that one. So green one is short one. This is shorter. And the blue one, which is that one, is longer. So in such a case, if I would like to use the power, let's say the geometric series, so should do this as follows. I continue. This is 1 over 2 pi I. I take gamma 2, Fw I copy, and here I pull out the longer. Which one is the longer? The longer is the W. So put here W minus Z0, and here I'm getting 1 minus Z0 divided by W minus Z0 dW, and I recognize that this is my Q. Q is smaller than 1. Okay, so I will be using the geometric series here. And we have also minus, sorry, this is minus. And 10, we put it like this. This is minus, don't forget it. And I have gamma 2, and this is Fw. And now let's look here. This is the second one. So let me choose some color, just for the purpose of yellow maybe, like this. Okay, and let's look I have another distance. I have here an element for the second interval. It's on the gamma 1, so W is here. Maybe I should write it down differently. W is on that line. So if I look at this distance, I have that distance and the green distance. So now green is longer and yellow is shorter. So in order to get the proper geometric series, so I have to do exactly opposite. So this one is clearly shorter, and that one is longer. Maybe use the red one, shorter. This is shorter, and this one is longer. So that one is shorter, that one is longer vector. So therefore we will pull it out differently. I put here that one Z minus Z0, and then I'm getting 1, and then I'm getting W minus Z0 divided by Z minus Z0 minus 1 dW. And then, yes, geometric series, yes, we will also use here the geometric series Q. So that means this is my Q for the second integral. So continue, and we continue, write it down. This is 1 over 2 pi I, and the integral is gamma 2, and this is Fw. And then I do the power series, so just simply, since we did it a couple of times already, so I will write it down. This is equal to Z minus Z0 to the power n divided by W minus Z0 to the power n plus 1. This is dW. And for the second one, look, here I have minus, so if I reverse this 2, so that minus and this reversion will cancel each other. So that means actually I can write here plus 1 over 2 pi I integral gamma 1, and then I put here f of W, and here we have the power series, and this power series looks similar. N is equal to 0 to infinity, except it is W minus Z0 to the power n, and this is Z minus Z0 to the power n plus 1 n plus 1. Very good, and then of course dw. So the next step is the following. We can actually enter the integral inside. So let me write it down. So let's say we can interchange the integration and the summation. So that means we can interchange this and we can interchange that. So let's do it. So we are getting, this is 1 over 2 pi I. And then I put this series out. This is n is equal 0 to infinity. And then I put here integral here. This is gamma 2. And I put here f of w. And this is w minus z0 to the n plus 1 dw. And times multiply. This is z minus z0 to the power n. And that's my power series. So this is the part of which is the power series. And the second one is again the same, 2 pi I. And now that one, let's arrange it. This is n is equal again 0 to infinity. So integral gamma 1. And then I have here omega minus z0 to the power n times maybe f of w times omega minus z0 to the power n dw, and this will be z minus z0, sorry, 1 divided, so 1 divided by z minus z0 to the power n plus 1. Okay, so that's, you see, those are the positive powers. And those are negative powers. So maybe let's re-index it just to write it down correctly. So my reindexation will be like this. I will just call this one n plus 1. I will call it, let's call it sorry, this is k. Sorry, not minus, just k. K. So that means n is equal k minus 1. K minus 1. So I can reindex them and notice a couple of things. First thing I notice that since this integral, this is a f is analytic. So put it blue. So this integral and that integral do not really depend on the path of integration. Gamma 1, gamma 2 doesn't really matter because there is no more. This is just simply an integral, well-defined an integral. So by the fact that two homotopic contours gives you the same integral, I can replace both by gamma. I will replace them both by gamma. So gamma 2, gamma 1 replaced by gamma. The gamma, which is the one that we just took here in the very beginning, any contour like a circle, not necessarily even a circle, but it can be any contour. So I can continue my consideration here. So I get in here, this will be like a positive, so this is n is equal 0 to infinity. Then I have here 1 over 2 pi I. This is gamma, and this is f of omega, and this is omega minus z0 n plus 1 d omega, and that one is z minus z0 to the power n. So that means simply that this is my coefficient an. an for n is equal to 0, 1, 2, etc. And then we have also plus. This will be plus, and this is plus, and I have another series. So now this time, you see if k is equal to 0, if n is equal to 0, then 1 second. If n is equal to 0, k is equal to 1. You see, n is equal to 0, then this one is, so we begin here. So let me put it like that. I will put this one here. So I put it like this. K is equal to 1, and this will go to infinity. And then I'm getting here, this is integral, this is f gamma, and this is f omega. And I can rewrite it down. I rewrite it. This is minus z0, and what do I get here? I'm getting here that this will be how much? So if n has to replace by k minus 1, so this means this will be equal to k minus 1. And here I have here the power, and this will be z minus z0 to the power k. Oh, and now, good. So what does it mean? Let me check if everything is correct, because I put this one minus n, oh, plus 1, very good, plus 1. Why? Because you put it there down, I put here like this, I write it down like this, so I put here w minus z0 to the power n is equal to 1 divided by w minus z0 to the power n, and in such a case, I'm getting here, this one is equal to, and what is minus n? This is equal, and this one is equal to, yeah, minus k plus 1, yeah. So this is minus k, and this is k, minus k, this is minus k, please make sure, minus k plus 1. So I'm getting here, this is 1 divided by w minus 0, and that one is n, so this is minus k plus 1. Very good. So that is my coefficient, which will be equal a to the power minus k. This is my coefficient k. Yeah, and almost done, because we already got everything. We just need to rewrite it properly, so it will be written. Let's use one notation, n is equal minus infinity, infinity, and then we are getting here gamma, and I just simply replace integers which were positive now by negative, so that gives me exactly the formula. Minus k becomes now, let's say, if n is negative, so just put here minus k replaced by n, so this will be equal to z0 to the power n plus 1 dw times and this will be z minus z0, and power can be negative. So that is my Laurent series coefficient an, and this is exactly how it was postulated in the formulation of this theorem. So maybe the theorem is proved, and immediate consequence. So put it like this. So corollary. Generalization, so of the Cauchy inequalities. So generalized Cauchy inequalities. So suppose okay, f of z is an analytic function in annulus, in the annulus A equals, and this will be z such that R1 smaller than z minus z0 smaller than R2. Yes, and let gamma will be just simply z0 plus r EIT. So that's the circle inside this one. So this will be t belongs to the 0 to 2 pi, such that R1 smaller than R smaller than R2. Then we have that f of z can be represented as the Laurent series, and we also have the estimate on the coefficients, namely that an will be smaller equal than m, I will explain, r to the n. So that's the same thing, where m is equal maximum for z minus z0 is equal to r of f of z. So that's the same thing as we've seen in the case of the power series, but now it is actually applied to the Laurent series, still true. So for the Laurent series, still true. Notice that in the case n is negative, so that's not exactly the division, it's just multiplication by the power, by the positive power of r. So maybe a little proof, just to show you that we are actually do not lie to you. So here we have here this formula, so write it down. We have here that an, I can rewrite it, the absolute value is 1 over 2 pi I, integral gamma, and what do I have here? I have here fw, and this is w minus z0 to the power n plus 1, and this is n plus 1. So put it again, n plus 1. This is dw, and now I can rewrite it down. This is smaller equal 1 over 2 pi, and this is again gamma, but now I'm changing this integral to the integral dw, so this is a different line integral. Put here like this, omega minus z0 to the power n plus 1. But here, of course, remember, this is again, let's go to the picture. So this is your gamma, this is your z0, omega is here, so that length is small r. So that one is equal 1 over 2 pi, and that one is equal gamma, and that one is equal to fw, this is dw, and that one is nothing else than rn plus 1. But now we have here that fw is smaller equal than m. Why? Because that's the maximum. That's the maximum. This is the maximum. So what can I do? I can just simply replace it. So let's do it. Smaller equal, this is 1 over 2 pi. Take this one out. This is rn plus 1. Did I do something wrong? Yeah. R. Wrong R. Of course, you see. So this must be Rn. Of course, Rn. Yeah, because that's the same radius as it is here. Okay, Rn, and then you have here integral, and this is gamma, and this is d double gamma. So what is the length of this circle? Okay, this is equal 1 over 2 pi, 1 over Rn plus 1, 2 pi R. It's not writing nicely, plus 1, and this is 2 pi R, and we are getting this is equal to m. I forgot m. Now it seems to be okay. You see this one we replace by m, so that one goes here. Then I'm getting what I'm supposed to get. That comes. Sorry, this cancels that cancels that, and we still have here m. So we are getting m divided by r to the n, and we achieved our goal. We proved the Cauchy inequality. So maybe yeah, that this one is actually is kind of a cool, because now maybe I change the page and let's go to the next page. We can actually ask ourselves how to integrate Laurent series. So how to integrate Laurent series? How to integrate Laurent series? Question mark. So let's say, so this is my annulus. Call this annulus A. So this is my A, and this is another circle, and this is the center, Z0. And now I have here a path of integration, any path. So positively oriented, like this. So to protect the contour. So put it like this. Gamma. And let's say like this. Let gamma be a simple, just for the simplicity, simple, closed, positively oriented contour surrounding or containing Z0 inside bounded by gamma area. So area, maybe I write it down for area. So that's exactly what is illustrated, what is shown on this picture. So this is not relevant, so you see, we just don't give it to people. So now I want to integrate it. So let's find the integral. Let's compute. Compute this integral gamma of f of z dz, and since here we have this representation, so again we are getting the integral of the Laurent series of that function. So this is n is equal minus infinity to infinity, and here we have a n z minus z0 to the power n. And then I put here dz, because that's the integral. Now, we already learned it. You can interchange the integration with the summation. You can interchange it. And then this will produce you the result. This will be nothing else, and this is sigma. N is equal minus infinity, infinity. And here we are getting a n, and here we have the integral over gamma, and this is z minus z0 to the power n dz. Now is the question, what is this? What is this? So recall. The function, so the antiderivative of z minus z0 is given by what formula? We know it. This is just simply z minus z0 to the power n plus 1 divided by n plus 1 for n different than minus 1. So if this function has an antiderivative, and this is closed contour, so that means that if n is different than minus 1, then this integral z minus z0 n dz is exactly z minus z0 n plus 1 taken from the beginning at z0 to z0, so it must be 0. So that's 0. So that means I can go back and I can write the answer. This is a minus 1, and this is integral gamma, and for minus 1 it will be dz, and this will be z minus z0. But then that one we compute from the Cauchy integral formula. So we continue with this is equal 2 pi I, and this will be a minus 1. So we just got the formula. So maybe I actually remove it. And make this one like an insertion. This we insert, and we continue this integral. So this will be equal, and this will be a minus 1 integral, and this will be gamma. And I cannot show it. I have to show this part. Gamma, and this will be dz divided by z minus z0. So now Cauchy integral formula, and we are getting the answer 2 pi I a minus 1. 2 pi I a minus 1. Very good. So we are actually, so you see, the Laurent series, maybe put it as a kind of a, remark or notice that the a minus 1 coefficient in the Laurent series, that a minus 1 coefficient in the Laurent series is actually giving us the answer to the integration problem, and that means simply that this integral over gamma f z dz is exactly equal to 2 pi I a minus 1, and this coefficient will be playing an important role in the further development of this course. So maybe let's concentrate our attention on the singularities of the function, or let's say analytic function. So we start with the definition. Suppose f of z is an analytic function we say that z0 is a singular point is a singular point maybe also in the bracket, or singularity of f of z. Now I can move up. If f of z is not analytic, at z0. And that means basically, which means one of two things, of two things, which means that that either z0 doesn't belong to the domain of f of z, or f of z is not undifferentiable at z0. And in this case, we understand differentiable, which means C differentiable. So maybe put it like this: C differentiable, C complex derivative. So, and this is basically the important part, because we are actually will be interested in the so-called isolated singular point. So put it another definition. A point z0 is called an isolated singularity, maybe like this singular point, or isolated singularity if, except z0, there are no other singular points in a neighborhood of z0. So that means I can just simply say, what is this neighborhood? If there exists an epsilon, so that's the radius of the disk, such that for every z satisfying the property oh, I should write it down. Singular point. Oh, I am so sorry. This is not correctly written condition. It's not erasing, so let me just cross it out. Cannot erase it. So let's say, put it again, start it again. You see, sometimes we have to do it twice. If you don't do it correctly, no. Definition. A singular point z0 of the function f of z is said to be an isolated singular point. again, doesn't matter, point, or isolated singularity, or isolated, or isolated singularity. So that's what I said. If this is the only singular point in the small neighborhood of Z0, so that means if there exists an epsilon larger than 0, such that for every z, if z is different, so that means this is different from z0 and smaller than epsilon, then f prime of z exists. So that means here we have this small neighborhood, we call it pointed neighborhood. We were using it some time ago, this notation. We denoted this like a pointed neighborhood, we call it D. We call it like a, this set we call D. This is called the D epsilon f z0, so that means exactly this set, and this is simply z such that 0, z minus z0 smaller than epsilon. So that means simply that f of z is analytic on this pointed, means you take out, you remove the point z0, and that means function is analytic, f of z. Analytic here. Not here, only here. Does not know, we have no value. So such a point is called, of course, once you have an isolated singular point, we have analyticity. So notice that this is an A, annulus. So for an isolated singular point, z0 of f of z, we have a Laurent series expansion. And this is exactly this series expansion. So let's write it down. And I will write it down in such a way that I will separate positive powers, let's say the power series, from the negative powers. Z minus Z0 to the power n plus, and this is the remaining part, minus 1 to the infinity. And this is A minus n, maybe, can I erase it? No. Oh, I can. Now it works. A minus n divided by z minus z0 to the power n. Okay? So there's nothing here. To the power n. So that is the power series. So we have this Laurent series expansion. So notice that this is a power series. This is the power series. Only z0 is missing here. This is for z, this is for z belonging to the d epsilon z0. So we have this d epsilon z0, this is the annulus. So the first part, actually, if you notice that one, this one, call this A, I call this A of z, because this is power series, so this is analytic. So this A of z, put it like this, A of z, we put it like this, call it, just separate them both, and this will be n is equal 0 to infinity a n z minus z0 to the power n. We'll call it analytic part of Laurent series, and this will be star, analytic part. Because power series, analytic series, series star. Because that's a power series and this is analytic. It's just even analytic at Z0. And this one, the other one, I call P, because this will stand, P of Z will be standing for all negative powers, minus 1 to infinity, and this will be a minus n, and the powers will be z minus z0 to the power n negative. And this we will call it principal part. Principal part of Laurent series star. So we put it here, we defined. We define. So this is principal part. And as you notice, principal part sounds already like a more important, kind of more important importance is there. So we have here, put it again, this is P of Z, that's a principal part. Analytic, principal. Analytic, this is analytic, principal. Very good. And now we'll introduce very important notion and put it like a definition. Suppose Z0 is an isolated singular point of f of z, and we will do the following. We will call Z0 a removable singularity if the principal part of its Laurent series center doesn't erase? P of Z, Laurent series P of Z center at Z0 is identically 0. That means it's 0, doesn't exist. So that means P of Z is equal to 0. There is no such a, all the coefficients are 0. So this will be called removable singularity. B. Pole if the principal part P of Z is different than 0, but it has only finitely many terms. And that simply means that this principal part in such a case can be written as, so let me write it down, this will be like a minus 1, and this will be Z minus Z0, plus a minus 2, Z minus Z0 squared. And the last one, and we assume that the last one is, this is Z minus Z0 to the power m, and here we assume that that one is non-zero, but all others are 0, so there is no others. So then in that case, in this case, and in this case, moreover, put it like this, moreover, if this is your principal part, then M, and this number M will be called the order of the pole Z0. So that means, in other words, Z0 is a pole of order M. So that's the form. And do I have any paper? We don't have any more paper. And okay, I have to do something about it. So, and then we have the last point. Maybe I squeeze it here. And essential singularity. If P of Z is infinite series. So if this is infinite, then this will be called essential singularity. And I run out of the space, so I have to finish it here. Thank you.